Hello everyone, this is the 5th episode of my vector series. We are going to talk more about dot product and vector projection. First, here are some dot product properties. Many of them are not difficult to prove. We are not going to show the proofs here. There is a link in the description below for the proofs of these properties. Let's talk about something more interesting. Here's a statement. For vectors u, v, and w in R3, if u dot v is equal to u dot w and u is non-zero, then v must be equal to w. Is that true or false? How about take a few seconds to think about this? Okay, time's up. We know if u, v, and w are real numbers, and the operation is usual multiplication in R, the statement will be true. But that's not the case when they are vectors. Here's the simplest counterexample. I dot j is equal to 0. I dot k is also equal to 0. So I dot j equals I dot k. But j is not equal to k. Know that u dot v equals u dot w only implies that u dot v minus w is 0. Meaning that u is orthogonal to v minus w. I also want to talk about vector projection. Here's the idea. A light source is directly above this vector, casting a shadow on the table. The vector projection is that shadow. So, how do we find this projection? Before we continue, please take a second to subscribe. Thank you. Take a vector u in R3. We try to find the projection of u onto v. So, we need two things, direction and length. So now, getting the direction is easy. The projection has the same direction as v. So the unit vector v divided by magnitude of v gives the direction. What about the length? Well, we know the cosine of the angle between u and v is the magnitude of the projection divided by the hypotenuse, which is the magnitude of u. Solving this equation for magnitude of the projection, we get this. And it's the length. So, our projection vector is obtained by multiplying the direction and the length. Just a note here. If the angle between u and v is obtuse, then cosine of that angle is negative. And the projection vector points this way. So that's our formula. For computational purposes, we can do a little bit of manipulations to obtain a formula involving a dot product. Okay? We call this cosine formula for dot product. We can replace this cosine of the angle by the formula and simplify. Then we have a new formula. Using the magnitude of the projection, we can show that the work done on an object by a constant force forming an angle theta with the displacement vector is the force vector dotted with the displacement vector. Why? First, we call that the work is defined to be F times distance d. As you can see here, the magnitude of the projection is magnitude of F times cosine of theta. And the magnitude of the displacement vector is distance. Multiplying them, we have the dot product. Okay, we'll talk about cross product next time. Stay tuned. If you like this video series, please give me a like, subscribe to my channel, and share my videos to others. I'm Wilson. Thank you for watching. I will see you next time.